Okay? Now, for one instance of this, if I was just making a frequency distribution, let's just to make up an example. Say I went to the hospital, checked out 7 newborns, and let's say 4 of them were girls. Okay? Well, let me put a 4 in here. Then we would come over here and put a tick mark right over here at 4. Okay? And if I were to perform this procedure again with another 7 babies, maybe at another hospital, I would find maybe only 2 of them are girls. So then I would come back here and put a tick mark here. Well, if I continue doing this procedure over and over again at different hospitals, checking out 7 babies, I'm sure, maybe get one here, and I'd have a number tick marks, and it would form. I mean, it would look like a normal distribution, but it really isn't. This is a binomial distribution. Okay. Very few times would I get none of the 7 being girls, and very few times, if any, would I find that all 7 of my 7 chosen newborns are girls. All right? Let's take another situation. Let's take a situation where we're just rolling a die. Let's keep it simple. We've got a 6-sided die, numbered 1 through 6, and the situation is I want to know whether or not I got a 2. And we're going to roll the die 5 times. And I want to know, out of those 5 times, how many times I got a 2. Is that a binomial distribution situation? Let's find out. Do I have a fixed number of trials? Yes. Remember, the trials are the action. I'm going to roll it 5 times. Okay, so n is 5. Every trial must be independent. Would you agree rolling the die 1 time has absolutely no effect on the outcome of any other times? Okay, so I've satisfied number 2. Number 3, there must be exactly 2 possible outcomes, success or failure. They said, wait a minute, I can roll 6 different numbers. I don't have 2, I've got 6. But look at the way I stated the problem. I want to know whether I got a 2 or did not get a 2. By the way I state the problem, I can turn it from being 6 outcomes into just 2 outcomes. 1, success, rolling a 2, failure, not rolling a 2. So in this case, it is binomial. And number 4, the probability of success must be the same for each trial. Well, we know the probability of getting a 2, it can occur 1 time out of 6. So, yeah, the probability of success would be 1 out of 6. Okay. Once again, for this one, when I would set up my probability distribution, I would number the x dice from 0 to 5, not to 6. X ranges from 0 to the number of trials. If I'm going to roll it 5 times, it's going to go from 0 to 5. And of those, I'm going to count, with one instance of rolling it 5 times, I'm going to count how many times out of 5 I got it 2. And once again, we would build up a frequency. We could build up a frequency distribution table, and from that, we could figure out the probabilities. But really, for a binomial distribution, these are all known. For a given number of trials and a given probability of success, you can actually look up in a table, or you can calculate. You can actually calculate all these, and we'll do this in a later video. Let's take a third situation. Say you're doing a political survey. All right, you decide to survey 10 adults, and you're going to ask them on Tuesday, when it's time to vote, are you going to vote for Ralph Nader for president? In case you didn't know what he was running for. Ralph Nader's running for president. You're going to ask, are you going to vote for him? Is that a binomial situation? Well, let's find out. Fixed number of trials? Yes, I said I was going to ask, that's my action, 10 different people. Okay, so n is 10. Every trial must be independent. I'm assuming, since I'm picking these people at random, that what one person says will have no effect on what anybody else says. I guess it depends on how I do it. If I ask them one at a time by themselves, then hopefully I would get independent answers. Therefore, we can say that, yeah, these are independent trials. Number 3, there must be exactly 2 possible outcomes. Yeah, they're either going to vote for Ralph Nader or they're not. 2 outcomes. Now, this is number 4, the probability of success. And let's define success in this case as, yes, the person is going to vote for Ralph Nader, where failure is, he is not going to vote for Ralph Nader. Do we know the probability? No, we don't. In my first 2 examples, those were from the classical type of probability. We could calculate them. Here, how do we figure this out? Well, if I really want to know what that probability is, and it is some probability, I just don't know what it is. So we have satisfied 4, I just don't know what the probability is. If I want to do it, I would have to survey a lot more people instead of 10. Say I surveyed 1,000, asked if they were going to vote for Ralph Nader or not. From that, let's say out of 1,000, let's say 11 people said yes, they're going to vote for Ralph Nader. Well, then I would have 11 out of 1,000. That would have my probability then. Finally, my random variable x would represent the number of successes out of n trials. Out of my 10 people, what I would keep track of is which one of these, and this would be numbered from 0 to 10 this time. I'd have 11 values, 0 to 10, and executing my procedure one time with 10 people, I would have 1 tick mark someplace between 0 and 10. And if I did this over and over and over again, I would build up a number of tick marks, very few zeros, very few 10s. Voting for Ralph Nader, yes, very few 10s. And it would build up again to look like a normal curve, but it actually is a binomial distribution. Now, let's do one more example. Let's say you decide to randomly select 8 cars that pass you on the highway. And you decide to say, how many doors are on the cars that I choose? Okay, let's take a look at it. We have a fixed number of trials? Yes, we're going to randomly choose 8 cars. So I've got 8 trials. N is 8. Independent? Yeah, pretty much. I assume that one car going down the road has nothing to do with any other car going down the road for the most part. So I can assume that my random selection does make it they're independent trials. Are there exactly 2 possible outcomes? Well, if I'm going to keep track of how many doors each one has, there may be 1 door, 2 doors, 3 doors, 4 doors, 5 doors. I suppose if a limo, it may be 6 doors, 7 doors. Sounds like I got many more possibilities than just 2 possible outcomes. So, nope. That will not result in a binomial distribution. I've got too many possible outcomes. How can I change it? Instead of saying how many doors did each car have, I can ask the question, does the car have 4 doors? So, either it does have 4 doors or it does not have 4 doors. If I state it that way, yes, then I've got my binomial distribution. Okay? And once again, the probability of success must be the same for each trial. Well, let's say I change my question to, does it have 4 doors? Do I really know what the probability is that a car going down a road, if I pick at random, is going to have 4 doors? Don't know what it is. It is some number. There is some probability. Just don't know what it is. I would have to do an earlier study with a lot more cars than just 8 and find out what the probability is of 8 cars or just any number of cars having 4 doors. Okay. And once again, my probability distribution table would be numbered for the X column from 0 down to 8 because I'm performing at 8 trials. Okay. This concludes my discussion on the basics of binomial probability distributions.